I have the pleasure to present you as the chairman of this first session of the day to Luis López Díaz. He is a full professor at the University of Salamanca in Spain. If I'm not wrong, the oldest university in Spain. It has more than 800 years, so it's a really old institution. He did his PhD there in Salamanca. He spent some time at the George Washington University, and after that he was a postdoc at the Cavendish in Cambridge University. And now he's back in Salamanca, and he has a growing and evolving group in theory of spintronics. He is one of the Spanish members of the Spintronic Factory effort, and I'm very pleased to give you the floor. Thank you, Luis, for chairing this session. All yours.
Thank you very much, Fernando, and hello, everybody. Good afternoon. It is my pleasure to chair this first part of the session and to present the first speaker of today, Joo-Von Kim. Joo-Von is a well-known theoretical physicist in our field. He works at the Center for Nanoscience and Nanotechnology, which is a joint research unit of CNRS and Université Paris-Saclay. Joo-Von got his PhD from University of Western Australia, and shortly after that, in 2004, he joined the CNRS, Université Paris-Sud, where he has remained since then. He's a member of the Novel Magnetic Devices group, and he leads the theoretical and computational work carried out in this group. His activities are mainly focused on nonlinear and stochastic magnetization processes in nanostructured materials, and it covers many different topics, such as domain walls, skyrmions, vortices, magnonics, etc. So today he is going to talk about a theoretical framework to investigate spintronics phenomena. And I want to thank him for accepting, participating in giving this lecture. And Joo-Von, you can share your screen and start whenever you want. Thank you.
Hey, thank you for this very kind introduction, Luis. And thank you very much as well to Fernando for giving me this opportunity to give this lecture, which will be on some theoretical aspects of spintronics, titled Micromagnetism and Beyond. And hopefully this will give you an idea of some of the things that we can do theoretically and computationally as well to understand experimental phenomena and also to predict new phenomena for our colleagues in experiments to test out. So throughout this call, I guess you would have seen already a wide variety of basic magnetic and spintronic phenomena. And basically the idea is that the interplay between electric currents and the kind of spins that are brought with these currents and magnetization dynamics, they offer many interesting perspectives for applications. Okay, so I've just noted some of these here. So for example, we have potentially some compact memory devices driven by spin transfer torque, spin orbit torques, and so on. And the way that these function would require switching magnetization from one state to the other. There are also possibilities to generate microwave devices, right? So spin torque oscillators. I believe you'll have some lecture on this shortly this afternoon. And there have been, in recent years, some efforts to push towards unconventional computing, whether it's using spin waves, for example, in magnetic circuits, or some more exotic schemes, such as skyrmions and so on. And so from a theoretical or computational physicist point of view, can we simulate the magnetic behavior in these systems efficiently and accurately? And so that would be of use to both experimentalists and to understand and develop new theories. And basically, this is the theme of computational spintronics that I want to talk about today. And it's really the idea is that we can bridge the gap between some fundamental theories, such as electronic structure calculations and really on material properties, magnetic interactions, for example, quantum transport and statistical field theories, bridge that gap between theory and experiments and the devices that I talked about on the previous slide, so shown on the right, and somewhere in between us, let's say computational scientists, we help bridge this gap, and so we facilitate the feedback between these two, which help to interpret experiments and also to focus theoretical efforts. And so, so the remainder of this talk that I want to give today, it will be divided into two parts. So at the beginning, I will talk about some typical computational workflows that we use in such endeavors, which basically consist of essentially three facets. So a pre-processing part, the actual simulation of magnetization dynamics using, for example, atomistic or micromagnetic approaches, and some kind of post-processing afterwards. And then what I thought I'd do is I would show you how we put these into practice by describing a number of case studies that I've been involved with in recent years, so namely nanocontact vortex oscillators, propagating spin waves in synthetic antiferromagnets, classifying some anti-scaling behavior, and estimates of thermal stability for magnetic storage, for example. Okay, so onto the computational workflow. So essentially, this is an artificial kind of a division, but it gives you an idea of the kind of steps that one needs to take when we're thinking about describing, theoretically or computationally, some spintronic device. Okay, so first of all, let's ask yourself, how do you want to drive the system? What is being driven? Okay, are you applying magnetic fields or currents, for example? If you're driving large current densities into a pillar, these things may have some non-trivial spatial dependence that you may have to worry about. Are there some non-trivial magnetic states that you have to worry about? These would serve as initial states to do whatever study you wish to do next. And of course, in most functioning devices at ambient conditions, then you have to worry about thermal fluctuation. So these are some things that you have to think about as inputs somehow to your system. And then ultimately, what you do next is, and you have to worry about, how does the system evolve? So once you have your initial states and you want to drive the system now. So how do you evolve the system? Well, this is done essentially in micromagnetism by solving the Landau-Lifshitz equation with dissipative torques. And this features really, this is the core part of the computation in most cases. And so that allows you to evolve the system from some prepared initial state to some state that is of interest to your study. And then finally, you have to think, what quantity do you want to get out of this? Which quantity do you actually measure? So most of the time, computational codes will just spit out what the magnetization profile is. And maybe that's okay. Okay, if you're working with microscopists, then maybe this is enough. If you want to know things like domain wall positions, skyrmion positions, whatever, these can be derived from a spatial, spatial profile of the magnetization. But maybe it's more complicated. Maybe you're working with, magnetic tunnel junctions, for example. Then you have to worry about some kind of spatial averaging. Maybe you're studying this in the frequency domain and not the time domain. Okay, so you have to think about how to get this information out of your simulation. And of course, if you're looking at spin waves or doing some kind of spectroscopy, then you're not really looking at real space necessarily, but maybe reciprocal space. And so then you have to worry about how to get this kind of information out of your simulation. So I'll talk about some examples during this lecture. Okay, so in terms of input, so how complicated can this be? Well, it depends really on the kind of system that you study. So if you have some kind of a realistic nanopillar geometry, so this is an example taken from Ricardo Hertel's paper, where he showed that if you model the real electrodes that you might have, so your nanopillar is kind of in here somewhere, then the current profiles can be quite complicated, right? They can be quite non-uniform. And associated to that, you might have some very kind of complicated Ørsted field profile as well. So if you wanted to model this accurately, then this is something that you have to think about. If you're talking about spin wave propagation within a wire, so this is an example from our colleagues in Strasbourg, where they studied spin waves propagating along this permalloy Y in the middle, where they used some antennas, meander type antennas here, as a way to excite and to detect the spin waves. In that case, your excitation profile may be non-trivial. Okay, so you're not just exciting with a uniform field, but you have to kind of worry about your antenna structure to kind of really extract out what kind of features are really going into the system. And if you're into, skyrmions, as a lot of us are, there is sometimes a need to kind of prepare these initially, because your ground state may be quite non-trivial, and so you have to worry about how accurately your initial state reflects what you might see in experiments. So once you have that sorted out, you go to your core kind of computational task, and that is simulating the magnetization dynamics. And there are two ways of basically discretizing the magnetization. So the first I'll talk about is the atomistic approach, where basically you try to model as accurately as possible the underlying lattice structure that you have of the system that you're studying. And so you would attach some magnetic moments to each point of the lattice. And so here's an example for a hexagonal lattice. And so this is, important when a lattice structure is important. So if you're, for example, studying maybe a 2D van der Waals material that's going to be talked about during the school, then maybe this is the way to go. Or when magnetic order maybe varies very quickly. So if you're talking about antiferromagnets and you have some staggered magnetization, then you might need to do it in an atomistic way. But the problem is that these things, because they're dealt with on the atomistic scale, it's really hard to kind of scale them up to maybe device scales on the order of microns. The more kind of maybe a common approach in Spintronics is use micromagnetics. And there what we do is we assume that the magnetization M can be described as a continuous field, M of R. Okay, so these are always normalized unit vectors. And then we can discretize them in some way. So one way, the simplest way, is the finite difference, where you just chop up your system into a regular grid. This is nice and easy, fast to implement. Not so good if you have some weird shapes. Okay, so obviously this is a rectangular grid. So if you have something that's not rectangular, it may not work so well. In such cases, you may go towards a finite element discretization. So this is now in a irregular grid. You can get away with fewer cells, better deals with arbitrary shapes, but the implementation is a bit more involved. But both cases are used quite a lot in the field. So, it really depends on the kind of systems that you wish to study. And so once you have all that sorted out, so we come to the part of the magnetization dynamics. So I mentioned that, this is the whole game is about solving the Landau-Lifshitz equation. And so there are essentially two types of terms on the right-hand side. So the first is this M cross H effective term that you've probably already seen. So where H effective is this effective field. And basically this effective field is represents some form of gradient in the magnetic potential energy U here, where U is actually an energy functional. So it's a function of a function. So it's a function of the magnetization field. Okay, and so this is a variational derivative. And so part of the game of this computational task is to really calculate everywhere in your system what this effective field is. Now, there are certain cases where this is very trivial. So for example, if you take the uniaxial anisotropy energy, so given here, so for example, if you have some easy axis along Z, it's just the scalar product of your magnetization along Z squared. So if you compute what the effective field is, then it just turns out to be just the Z component of magnetization oriented along Z. Okay, nothing very surprising. And this is what we call a local interaction, because it only really depends on what's happening locally. So if you want to calculate the effective field here shown in gray at some cell here at the center, well, then that really just depends on the magnetization at that particular cell. You make this slightly more complicated by looking at other terms which are non-local. So for example, the exchange interaction, which is obviously very important. So micromagnetically, this is expressed by some So if you want the effective field at this site here, well, you need to worry about what's going on with the neighbors, okay? And so in the lowest kind of approximation in a finite difference scheme, so this would involve a sum between what's going on in neighboring sites. And so depending on the accuracy that you want here, numerically, you can also take, next nearest neighbor cells or whatever, but, the idea is basically the same. Now we come to the hardest part, I would say, of micromagnetics. And it's probably the thing that actually makes this whole thing very difficult. And that's the calculation of dipolar fields. Why? Because dipolar interactions are long range. Okay. And so basically, if you want to know the effective field at a given point in space, you need to calculate over all the spins that exist in the system. Right? So the effective field at any point R requires summing over all the moments in your system. And so this is very time consuming, very computationally intensive. And so you can see this, if I write this out in the atomistic way, which is maybe something that's more familiar to you. So you have the total energy now summed over all the different spins in the system. And so you have, a simple kind of a scalar product between the two moments I and j, and then you have this kind of anisotropic term. But the point is that this, extends over all space, and you have to sum over everything. But in micromagnetics, what we do, we don't really look at it this from an atomistic point of view. We can take the micromagnetic approximation, and then you can convert this into a magnetic charge problem. And so you can write this dipole energy as scalar product of the magnetization with some dipolar field that is derived from this magnetostatic potential. And this potential basically contains two contributions. So a sum over the surface charges of any free surface you have in your system, and a sum over all the volume charges. And again, but you see that getting the potential at one point requires this integral over all space. And this is what makes this problem very hard. Now, just as an aside, there are ways to kind of speed up this calculation. And so, I'm not going to go through the details here, but in a finite difference scheme, so you can kind of rewrite this dipolar energy as a sum of as this following sum. So it's a product between the magnetization at a site I with this magnetization at site J, where this intervening kind of matrix of Dmag factors basically takes into account this kind of a shape anisotropy that pops up. And so what happens is that you kind of notice that this dipolar field is really just a sum over of all the moments in your system, but this is actually a convolution that is taking place, and so you can use a convolution theorem to kind of to speed this up. And so basically, you imagine that you can just take a Fourier transforms of these Dmag factors and the magnetization, so represented here, for example. So these F's are the Fourier transforms. Apply the convolution theorem, so you get the dipole field in reciprocal space, and then you back transform this into real space to get an estimate of what your dipole field should be. And why you want to do this is because it does help you gain in speed, because it scales as n log n, the total number of spins in the system, as opposed to n squared if you were to perform this sum explicitly. And I bring this up because nowadays there are some very nice algorithms to take care of these Fourier transforms on graphics processing units. And so these can help you really speed up the calculation, sometimes by a few orders of magnitude. Okay, and so let's now talk about the other term in the magnetization dynamics. So this gamma here, which represents dissipative torques. And so this basically represents anything that cannot be derived from a potential. So the first, maybe most well-known example is the Gilbert model for viscous damping. So this is a term that represents how energy, or models how energy dissipates from the magnetic system. And in what maybe is more of concern to participants of this particular school, if you're interested in spintronics, then you have current flows, you have spin torques. And so one form of the spin torques that is taken into account here is the Zhang-Li model, which basically describes torques that take place when you have, let's say, current flowing through a magnetic medium. And when you have gradients in the magnetization, you have these torques that appear. Okay, and so these can be represented in these two terms here, so often called the adiabatic and non-adiabatic torques. And we can note that here U is representative of some kind of a spin drift velocity. And the other form of torques that can appear in, let's call them current perpendicular to plane geometries, such as nanopillars, where you flow the current perpendicular to the film plane. And in such cases, you have potentially transfer of angular momentum from one layer to the other. And so these are described by this vector P. And so this is described by the Sonchulsky model. And so this also takes into account spin orbit torques, which will also be discussed later on this afternoon. And so basically the bottom line is that for most cases, a lot of the current induced phenomena can be modeled quite well using combinations of these torques. Okay, so the kind of last thing I want to talk about in terms of torques is thermal fluctuations. And so we can account for thermal fluctuations in micromagnetics by adding a random field to the effective field. Okay, so this is represented here by the lowercase h sub r. And so what are the properties of this field? Well, it has a zero mean, and it has a white noise correlation, so shown here. And so basically this just represents Gaussian white noise that is being applied to the magnetization dynamics. So basically, as you can see here, when you subject a spin to this random field, you'll have something that looks a lot like Brownian motion, but now it's for precessional dynamics. And it's something that's quite important to point out is that when you have such situations, and it is quite important to think about thermal averages, you really want to average over many different realizations of this, because as in the case for Brownian motion, you know, in physics, you know, a given trajectory probably does not mean much. It's really averaging over many trajectories that you are able to get something, you know, physical out. So all of these features described so far are available in a number of open source codes. So let me start with some micromagnetic codes which use the finite difference approach. So the most well-known and traditionally perhaps most used is the OOMMF code, Object-Oriented Micromagnetic Framework, which is developed at NIST in Gaithersburg in the US. And this is designed to be portable, extensible, and especially a robust reference for micromagnetics. So, you know, it features a graphical interface if you would want to go into any programming, you know, yourself. More recently, there have been some codes that now take advantage of GPUs. And so one early example is MUMAX3. It's available here. And so this offers a large speed up compared to traditional codes that just run on CPUs. There are a wide range of modules available, a graphical interface and some APIs for programming. And more recently, I'd like also to point out this code called Boris, which is also a GPU accelerated code developed at University of Central Lancashire, with the specific feature that they also integrate spin transport self-consistently. So that might be interesting if you you know, interested in studying really the interplay between spin currents and magnetization dynamics. On the atomistic side, the vampire code is also very useful if you're really interested in simulating, you know, true lattice structures, for example, flexible problem definition and GPU accelerated. And finally, there's also the Spirit code developed at the Research Center in Jülich, which has a very nice user interface and some interesting programming APIs. And of course, these are just examples. Of course, if you're a student working in a group with their own code, then please use the code of the group. You know, they'll have likely to have a lot more experts to help you out. So, but you know, for those of you who are maybe curious to kind of try things out, you know, feel free to check out some of these open source codes. They're pretty good. Okay, so once you have run your simulations, now you have to worry about what you want to measure, what you want to compare with experiments, for example. And so, as I said from the outset, you know, most of the time you will just have the magnetization state at the end, okay, M of R. And you need to massage this in some way to make it useful often, right? Now, if you're doing microscopy, so here's an example of a magnetic force microscope. image of stripe domains. It's actually fairly close to what's calculated. There might be some convolution with your MFM tip and so on, but you're getting pretty close to the final quantity that you want to compare with experiments. If you were doing, looking at switching in a magnetic tunnel junction, so this is an example of time domain measurements of switching in a magnetic tunnel junction, then you also have to worry about how you average the magnetization as a function of time to really make the correspondence with an experimental system. If you're looking at oscillators, for example, then you have to worry about not so much the time dependence, but the frequency dependence of what you've calculated. And like I mentioned earlier on, if you want to make comparisons with Brillouin light scattering experiments, for example, where you measure spin wave dispersion relations there, you have some incoming spin wave vector giving some frequency shifts. So from that, you can construct an omega versus k type of curve. Then you really have to worry about how one gets such quantities from your experiments. I'll give you an example later on of how that can be done. Okay, so so just a few words about the computational workflow. So let me now just talk about very quickly a number of these case studies where we put into practice, some of these ideas. And the first is the nanocontact vortex oscillator. So imagine, so this is the geometry of the device that was studied, a 20 nanometer metallic contact that is in proximity to a permalloy film, 20 nanometer thick here. And so basically we flow large current densities through this. And so the idea was that, well, okay, there was a belief that there's a vortex structure that kind of lives in this permalloy film. And your colleague, the experimentalist, comes in and shows you some of these curves. Okay, I've measured a lot of oscillations in this device, very rich. Can we understand this somehow? And so these are basically power spectra of the oscillations in this permalloy film, and taken at different currents. And so if you kind of sweep the current up, for example, you see a rich, variety of behavior that is not necessarily obvious, what's going on. And so, so what we had to do is to, first of all, model the current flow through these nanocontacts, and this was done with Console. So this is a finite element code, and so that basically allowed us to really detail the kind of current flows and the Ørsted fields that are generated in this nanocontact system. And this is a snapshot of the actual device structure. So you have an electrode on one side of the film, and so your profile is actually quite asymmetric with respect to the center. But anyway, you can get some detailed information about what's going on. And then so what you do is that you put all this information into a finite difference scheme, and you stick that into Mumax, and so that is your input drive. And so, so this is what it looks like when you drive the system. And so you have this vortex that is gyrating, and so what we did was to simulate at a given current the dynamics over 200 nanoseconds. And so you can see that some kind of funny things go on. You just saw a vortex core reversal event. Here's another one, and so basically for a given current, we simulate this over 200 nanoseconds, and then proceed with the next current by using the final state of the preceding current. And so basically what you can get out of this is that you have some kind of a spatial average of the magnetization as a function of time, that you take the Fourier transform of, that gives you that you have some kind of a spectral power in some frequencies. And from this, you can construct a color map of what kind of oscillation frequencies are going on in the system. And so, so this is what you get. You're quite happy when you go back to see your colleague, the experimenter, say, look, this is what I simulated. We did as best as we could to model the system. And, actually, surprisingly, maybe we got lucky, but it works quite well. So you see all these different branches that come off this main branch. This is due to the core reversal process. So not only is it qualitatively similar, but quantitatively actually pretty good as well. So, this lower branch here is at 200, just about 200 megahertz, which is what we find in simulation. And if you look out here, close to 16 milliamps, you have something around 600 megahertz, which is exactly what we also find in simulation. So that basically just shows you that, sometimes it's actually quite important to really account for your device geometry. Second case study, spin waves. So in this particular example, spin waves in a synthetic antiferromagnet. So what we have is two ferromagnetic layers essentially, which are coupled through this antiferromagnetic RKKY coupling. And the other feature that we wanted to look at was, what happens if you have a domain wall in such an antiferromagnet. So not only do you have this antiferromagnetically ordered domains here, but you also have coupled domain wall systems. And so we're interested in studying, what kind of spin wave, what kind of spin waves would propagate in such systems. And so, okay, so again, so you need to prepare your system. So you start, in this case, it's not that complicated, but you relax the system to find your ground states. And so this is the top view, showing the basically the top view of this structure with a domain wall running down the middle here. And so that's the top layer and that's the bottom layer. And so you have some periodic boundaries running upwards so that we allow waves to kind of propagate freely in this vertical axis. And what you do to excite spin waves is the following. So we looked at two different points in space. So one point here at the domain wall and one point in the domain. And so the way you excite a spin wave with a given wave vector is that you just define spatially some kind of a wave profile for your excitation field. And so this is shown schematically here. But you give this excitation field a pulse in time, okay? And so when you do that, you basically impose a wave vector, but you pulse it in time. And so if you just look at a point along this dotted line, well, the magnetization is going to oscillate and it's going to decay in time, so as shown here. And this oscillation frequency is basically going to give you the frequency of this particular spin wave, right? And so the post-processing in this case is actually very similar to the previous case. So you make these measurements in simulations. You go through the different wave vectors you can fit into your system. You hit it with a pulse. You measure what the frequency is, and you collect up all these different Fourier transform data. And this is what you find. So if you're in a domain, so along this line here, so here's frequency as a function of wave vector. You can pick out these calculated dispersion relations here. So you have two branches. They're basically the dipolar shifted branches of your top and bottom layers. And if you look at the domain wall here, then you see something that's quite asymmetric. And so this is actually well known from domain wall theory that you have these channeled spin wave modes. So this is a way that one can get access to a spectroscopic kind of a measurement. So frequency as a function of wave vector based on a micromagnetic code that just computes M of X. Okay, so the third case study I'd like to talk about is something a bit more maybe non-conventional in the sense that we try to use some of the more modern techniques of computation, and that is the machine learning. And the context was the following. So we were interested in looking at atomistic spin dynamic simulations of this bilayer system. So palladium ion on iridium 111. With the specific feature that it's actually a frustrated magnet that supports skyrmions and anti-skyrmions. So these are antiparticle kind of equivalents of skyrmions. And so this is a schematic of the system that we wanted to study. So you have both skyrmion states are shown here, highlighted by the purple, and an anti-skyrmion state here, and so highlighted by the green. And so the idea was, okay, well, let's look at what happens if you apply current. So we imagine that you apply a current through the substrate through the iridium 111 substrate. So this generates spin orbit torques that we can model using the Slonczewski model, as I described before. So here you'd have a field-like and a damping-like contribution, and basically the study was just, okay, let's see what happens with these two with these two types of skyrmions. And what we found was that, the skyrmions, nothing really interesting happens. They kind of just propagate as you would expect them to. Whereas for the anti-skyrmions, what was kind of intriguing was that depending on how strong you can apply these currents, you might get very different trajectories. Okay, so here are the three kinds of trajectories that you find. So one is what we call a linear trajectory. So if the anti-skyrmion starts here in the center, well, it just deviates linearly along here and just basically continues on a straight line until your simulation stops. If you kind of increase the current densities a little, then it kind of starts on this trajectory, but then deviates around here, like such as this, and ends up going towards the top left. So this is what we call the deflected regime. And if you increase the current even more, you have something that's called trochoidal. So this is shown here in the light blue, where the trajectory kind of executes this trochoidal motion indefinitely. Okay, great. So this was quite strange. The problem with constructing a phase diagram is that you need some kind of way to classify what these are. Right? You can run hundreds of these simulations, but if you don't want to look at each one one by one, you need some kind of technique to classify them. Right? So here's an example of the different deflected motions that comes out of a simulation. So these are just superimposed on each other. Visually we can say, well, they're quite similar. But telling the computer that this is one family and the set of trochoidal trajectories here is part of another family is actually not trivial. And this is where we appeal to machine learning to help us out to classify. And so the way we did it was the following. So so the challenge is to can we get the machine to classify this for us so that we can just do something else, like write papers or something. And so the idea was the following. So you take, with any kind of machine learning process, you take a subset of your data and you use it as a training set. And so this is what the training involves. So we took, examples of a linear, of deflected and trochoidal behavior. And we said, okay, well, we're not going to look at the trajectories directly, but we'll map the orientations of this propagation onto the unit circle. All right. We don't really care how far it goes. We just want to know in which direction it goes throughout the simulation. And so when you do this for the linear case, you see that, well, you don't see the full circle because the points basically only indicate that during the simulation, it only went along this direction. So basically what happened was the anti-skyrmion probably did something like this. It curved initially, and then it ended up at some steady state direction. But anyway, this is what gets out of it. This is what this processing tells you. When you have the deflected case, so the motion kind of goes like this and goes upwards here. So basically, it in terms of the velocity orientation, it starts off here, goes around this on the unit circle, and basically ends up here. All right. And for the trochoidal case, it kind of loops around all the time. So it actually does the full revolution of the circle. And so you would have, if you convert these trajectories onto the unit circle, you'd have something like this. You'd have full circles. And so this was, this is the training set now. Let's see if this works. So we used such images. You convert the trajectories to such images, and you use these as a training set. So this is linear. Let's call this light gray. Deflected, medium gray, full circle, dark gray, and you just throw it at some machine learning algorithms, like for example in Mathematica, and it gives you an example of how did it classify, and it turns out it actually works quite well. So perhaps you can't see it so well, but basically here we superimpose the computed unit circle projections and the trained cases, and basically it matches up quite well. So trochoidals, full circles are always in dark gray. Deflected cases, half covered circles are in medium gray, and the other cases are in light gray. And so basically this allows you to apply this recursively to refine the phase boundaries of the phase diagram that you want to construct. So you don't have to actually literally scan through point by point your phase boundary, but you can do a rough scan, use the machine learning to kind of tell you which part of the, which phase you're in, and then recursively mesh out your phase boundary. So this is what we did, and this provided a huge gain in computation time because we didn't need to simulate all points in phase space. And so the last example that is non-trivial that I'll talk about is the case of thermal stability, because this is something that is actually quite important in magnetic storage applications, where basically, the rule of thumb is the 10-year thermal stability for a given magnetic state. Now, calculating this is actually very challenging because, 10 years is about 10 to the 9 seconds, whereas your typical time scale of precessional dynamics of a Landau-Lifshitz equation is the order of nanoseconds, or maybe, fractions of nanoseconds, picoseconds, whatever you want. And so there is a big, almost 20 orders of magnitude between the two. And so you can't really just simulate this directly. And so, this is a real, computational challenge. And so what we explored recently was this method called forward flux sampling, which allows you to essentially estimate the rate or the stability of a magnetic bit. So based on a method of path sampling method for rare events. So basically, the prototypical problem is this: you have two equivalent magnetic states. Let's call them A and B. If they're in a perpendicular magnetized nanopillar, so then A might be pointing upwards, B is pointing downwards. There's an energy barrier that separates the two, and you want to know, well, if you're in the state A at 300 Kelvin, how long can you expect that to remain in the state A, right? This is the whole data storage challenge. Computing this is a challenge. So we use forward flux sampling, and the way it works is the following. So you have, so the way to imagine this is that you have some kind of trajectory that takes you from A to B. Okay, so from one state pointing upwards to one state pointing downwards, going across some energy barrier. And in this particular case, it involves nucleation of a domain wall and a propagation across the dot, as shown on the top here. And so you want to calculate what this rate is, K A to B. And so the forward flux sampling technique works as the following. So you imagine that you have a number of virtual interfaces that separate A and B, okay? And the rate, K A to B, can basically be expressed as a product of two terms, of phi A0 times PB, okay? So phi A0 is basically a measure of the flux from your initial basin of attraction, your initial state A, to your first interface, okay? I'll describe in more detail what that means. And P of B is basically a sort of cumulative probability, which basically, so it's given here. So it's a product of the set of probabilities, and each probability basically means that if you started at some interface I, what is the probability that you're going to get to the following interface? Okay, and so really this is just a way of building up in a sampling way, what the overall probability is for getting from A to B, under finite temperatures. So how does this work, in micromagnetics, let's say? Okay, let's first calculate 5A. So basically, you start, let's say, in mz plus 1, pointing upwards, and you want to know what this flux is. So the flux from A to 0. And so basically what this means is that you have to launch, let's say, m Langevin dynamic simulations. So let's say 1,000 typically. And so these are, what I mean by that is Landau-Lifshitz equation with random thermal noise. And you just run these systems and you stop when you get to interface lambda 0, right? You stop each simulation, they're going to take different times. You stop them when it reaches lambda 0. You save the states at lambda 0. And so the flux is basically going to be given by the total amount of time that you needed for your simulations to get to this first interface divided by the number of simulations you ran. Okay, so if you took, if all your simulations took, a few microseconds, then you divide that by m, 1,000 in this case, and this, so your flux would basically be number of traversals per unit time, okay? Next, what you do is that now you start at the interface from these saved states, let's say at interface 0, and you do the same thing again. Now you're going to run m non-Joo-Von dynamic simulations, and you will stop when you get to lambda 1, okay? And this is called a successful traversal. You did it. You managed to climb the energy barrier. You go to the next interface. If that happens, great. Save that state at lambda 1. What will happen, though, a lot of the time is that it doesn't manage and it just falls back into this basin of attraction, the initial state. So that fails, but that's okay, right? You note that down. And so the probability now of going from, let's say, 0 to 1 is basically the number of times you had a successful run out of the m attempts that you made, okay? Then you just repeat the same step until you get all the way to the B interface. You apply this formula and you have this basically transmission probability, if you like, all the way through to B. And so, okay, we did this for a number of different parameters. So here we vary DMI, for example. And one of the things we found was that, a lot of the time we would use the Arrhenius law to talk about thermal transition rates and so on. And so there's this attempt frequency and some exponential term with the energy barrier and KT on the bottom. Most of the time in magnetism, we'll just say, well, F0 is some number. That number is usually about 1 gigahertz. And so what we found was that actually that's not always true. And so if you look at these calculated lifetimes as a function of D, well, you see some, exponential decrease. That's fair enough. That is expected because, we're reducing the energy barrier. But if we really compare, the calculated lifetimes with what one would expect from this Arrhenius relation here with a constant attempt frequency, then that would be the black line, which is precisely what we do not see. And this is the case for, we look at different cases, we would see that the Arrhenius relation would always overestimate thermal stabilities, whereas the forward flux sampling will give you something slightly different. So anyway, so this is an example of, how far you can really push such simulation codes to really address, some really challenging problems, for example, in magnetic storage. And so just on the side here, I've shown you some of the calculated average, magnetic states that come out of the simulation, and just basically reaffirms this picture of a domain wall propagation as the most probable switching mechanism. Okay, so I think my time is up, so let me just summarize. So I just wanted to give you an overview of the different possibilities that computational micromagnetism offers, to interpret not only experimental data, but to also predict new phenomena, so you can suggest ideally new experiments. There are quite a few efficient atomistic and micromagnetic open source codes that are available, for you to try. Of course, those who are working in theory or computational groups, you probably have your own code, which is of course perfectly fine. But for those of you who just want to, try some of these things out, please download them and give them a go. And of course, a lot of the time the challenge is really to combine, these open source codes with sufficient pre or post processing to really obtain the quantities that you want to measure. And so let me just summarize by saying that, well, there are still many creative solutions out there that await the physical problem that you wish to study. So with that, thank you for your attention.
Okay, thank you very much, Joo-Von, for this very comprehensive and pedagogical lecture, for showing us the basics of the theory, and then also showing us some examples of the nice things that you can investigate with the theory. Okay, so we have about 10 minutes for questions. Let me go through them. So Jose Angel Fernandez Roldan is asking, he's saying thanks for the nice talk. And he's asking, how do you excite every frequency at once in case 2? Is it with a current pulse similar to a sinc function?
Yeah, that's an excellent question. So let me just bring this up. Yeah, you can do a sync function. That would be this would be a way to go. Yeah.
Okay, so let's move on to the next question. Ricardo is asking, where would you mark the limit of validity of LLG-based simulations?
Oh. Okay, so all right, LLG right in the middle. Well, magnetization is conserved, so you know it's really cases where you know this is true. Of course, there are maybe some kind of funny, you know, more exotic things like you know, inertial terms that you know people are seeing, but you know, for at least the precession part, you know, this comes from quantum mechanics, right? I mean, this is just precession in a field, so this is pretty good. What might be debatable is what we put as damping, what we put as, you know, spin torque or spin orbit torques, you know, depending on how elaborate or advanced the theory is. But I would say that today, you know, it's within it's a very good approximation for things that are studied experimentally. I suppose, you know, if you're looking at ultra fast processes and things like that, you have to be more careful. But let's say anything in the gigahertz type regime, that's probably fine. Right?
Okay, thanks. So next question says, thank you for informative talk. In case of spin torque oscillator, one also excites spin waves with a DC applied current. You showed about studying spin waves while exciting it with a periodic field. Is there any way possible to study micromagnetically the spin waves excited by a DC current in STNOs?
Yes, the short answer is yes. I mean, okay, so you know, this is a geometry that has been used to study spin wave excitations with a direct current. So I mean, if you get rid of the vortex, then this is certainly one operation mode. It's really the same process. So you look at a precessing magnetization. Now it's going to be in the gigahertz or the tens of gigahertz range. But essentially the process, you know, the computational process is identical. There's no problem with that.
Okay, so Ming Feng Shen saying thank you for your great talk, Professor Kim. In slide 21, what causes the two modes, spin wave in domain walls? Why one mode goes to higher frequency while the other one goes to lower frequency? And this effect exists in all magnetic domain walls or just in synthetic antiferromagnetic domain walls?
Okay, so if in a normal domain wall, a block domain wall, so this theory is known from, I think, the 60s or something like that. It's known that there is some zero gap, essentially a zero gap spin wave mode that is confined. In this particular example, we see two because it's a synthetic antiferromagnet and there's also DMI and stuff. It's actually a quite complicated system, so that's why it's not symmetric. But this lower, it's basically should be like almost like a quadratic function. This lower branch here goes very close to zero, and this high order one comes about because we have a synthetic antiferromagnet. So I hope that answers the question.
Okay. David Salomoni is saying, thank you, great talk. And then is asking, how would you model magnetization time reversal dynamics considering spin transfer torque current and femtosecond laser pulse heating acting together? Is it a problem for simulations that the time scale of the two driving forces are so different, nanoseconds for spin transfer torque and femtosecond for laser? Is atomistic model needed?
Yeah, excellent questions. I think maybe there isn't a clear answer to that. That's an active field of research at the moment, and the point of the time scales is actually very important. I would ask. I don't work in that field, so I can't really comment directly. But again, if you're thinking about the pre-processing inputs part of the talk, what you have to ask yourself, what is the laser doing? Is it just heating up the system? Well, in that case, okay, just add some temperature. If it's a bit more than that, are you are magnetic parameters changing because do you still have the same exchange? You really have to worry about these kinds of questions, and so that is probably a problem that needs to be addressed before you think about the simulation, because we can always simulate something, but it has to make sense. So but yeah, it's true. Femtosecond nanos, yeah, yeah, it's challenging, but probably doable. Yeah.
Okay, thanks.
Yeah.
So next question is actually two questions. What happens when you use a micromagnetic model with atomistic simulation? And two, what are the limitations of forward flux sampling method?
Okay, so first question on micromagnetics and atomistic. So was the question, can they be combined? I recall, Ricardo Hertel in Strasbourg, he showed once that he could combine, because he was worried about vortex core processes and things like that, and that really occurs on atomistic scales, and there's a way to kind of use an atomistic kind of description just for that part, and then finite elements, kind of match that onto a finite element thing, and just for the rest of the system. Mm-hmm. So there have been some efforts to do that, but that's quite involved. Concerning forward flux sampling, it's very long. It's a very long process. It requires a lot of parallel processing, and it could be, parallel. It could be very stupid parallel, like running things literally on different machines at the same time. But as you saw, you do have to do a lot of averaging, and we're talking about thousands and thousands of Langevin dynamics runs. So it works fairly well for small systems, but when you start to get much larger systems, then it might get a bit difficult. But at the same time, there aren't many solutions, So this is something that's straightforward to implement, at least.
Thanks. So next question is by Muhad, thanking you for the presentation, and then he asks about the skyrmion anti-skyrmion system. You showed some fancy trajectories exhibited by these features. So while looking at the abstract of the reference cited in the slide, I noticed that there is a core deformation. Are these trajectories due to the field-like torque effect?
Okay, so I probably cannot go into the details so much. So these trajectories come about because spin-orbit torques are, the direction of propagation depends on a property called a helicity. So maybe the easiest way to think about, so for a skyrmion, what the helicity means is that, is it a right-handed nail, a left-handed nail, a right-handed block, a left-handed block, okay? And if you put these four types of skyrmions under a given spin-orbit torque, they will move in different directions. They will not move in the same direction. For the anti-skyrmion, we don't talk about left-right block because the structure itself has both nail and block axes. And so the helicity is basically how this thing turns in space. And these trajectories come about because the helicity is being activated by the spin-orbit torque. So it's actually different for these different cases. And similarly to Walker breakdown in domain walls, at some point it kind of goes back and forth above the Walker transition, and this is really equivalent to that. So that's maybe the shortest answer I can give.
Thanks. Okay, so it's already 4 o'clock, so I think we should move to the next speaker. So I want to thank you, Joo-Von, once again